Today we're going to start the material for exam 4, and that will cover chapter 6 and 7. So we'll do chapter 6 today and chapter 7 on Thursday. Get that out of the way. Good. Yeah. There. All right. Right. Up to this point, we've learned how scientists make measurements. We've learned the vocabulary of chemistry, which is we've learned the alphabet of chemistry, which is the symbols for the elements. We've learned the vocabulary, which is writing chemical compounds. And now we're going to learn how to build sentences in chemistry. That is, how to write the chemical reactions and what they represent. Okay. Historically speaking, natural philosophers, that was the term coming out of medieval into the modern times. People who were interested in nature and how things worked were called natural philosophers. Then over time they specialized, but natural philosophers were jacks of all trades, and many of them were what we would call today chemists. And they were looking for, first of all, they were looking for evidence of the changes that we see in chemistry. One substance to another, a change in identity. And that's what we're going to look at first, right? What were some of those evidences for the chemical changes? Many of those signals were visual, which makes sense. Humans are visual creatures by and large. So you would see things like color changes, or evolution of a gas, or maybe formation of a solid out of a combination of liquids that had no solids in them before. When you put them together, you form a solid. We call that a precipitate. Of course, these changes are not always visible. Sometimes we have other senses involved, like a reaction may generate heat or might get cold. It's less likely that you will hear something that you don't also see. Like if you see gas forming, you'll probably hear a fizz. Let's see. Some of them might have tasted some things, right? But pretty soon they learned which ones they could and couldn't taste. And then, well, those are the main ideas. So I've mentioned these already. Color change, solid formation or precipitate, gases formation, or heat. And sometimes you may even get an open flame. For instance, if we combine potassium metal with water, it will generate hydrogen gas, and it will also generate massive amounts of heat. So much so that when the gas evolves and reaches the surface and mixes with air, of course, it has that oxygen and hydrogen, and then there's sufficient heat from the reaction to ignite the flame. So you will see potassium in water will not only generate gas, but it'll also burn. Okay, so these are various clues that chemical reactions have occurred, and you see, you witness a change in identity. In this case, this example, we have water, which has probably just a slight amount of acid in it to make it conducting. Right? If you pure water. Oh, okay, got another zoomer. Okay. Pure water is an insulator. It will not conduct electricity. So you add a little bit of acid, doesn't matter what kind, weak acid is probably safer. And then you drop this 9-volt battery in the water, pretty soon you see bubbles. There's a chemical reaction going on there. You're taking water and splitting it apart and making hydrogen gas and oxygen gas. So in this case, we see the formation of bubbles. That's our evidence for a chemical reaction. Here we have color changes. Okay. Here we have hydrochloric acid is added to a solution of cobalt-2 nitrate, turning the solution blue. So I assume this is the cobalt-2 nitrate. Here we've added acid to it, and here's the finished product. So the blue color is evidence of a chemical reaction. Right, color change. Here we're adding sodium dichromate, a solution of sodium dichromate, and we're combining it with a solution of lead nitrate. And in that case, the lead and the chromate combine, right? They're separate before we add the solutions together. Then the lead and the chromate get together and they form this yellow precipitate. Okay, so what we're doing there is forming a solid. That's more evidence that a chemical reaction has occurred. Now, when we write a chemical reaction, by convention, we always read the reaction from left to right. So the reactants, those that haven't changed yet, are the ones we put together. In this case, methane and oxygen. And when we put them together under the right conditions, they will react and produce products, carbon dioxide and water. So if you were in one of my classes that had a lab with it, we would learn how to use the Bunsen burner, which uses natural gas, which is primarily methane. And this is the reaction that would occur. Plus, it generates a lot of heat. So not only do you can you witness a change in products, the evidence of the products, but you also feel the heat. Now, you can't detect the carbon dioxide. It's a colorless gas, so that goes without saying. But you can put something in the way of the flame, like a test tube. And the cool test tube will take that water vapor and condense it. And you can see the vapor condensing on your tube before it gets too hot and then it vaporizes again. So you can see some evidence for this chemical reaction. And we always put an arrow in the middle showing that we're moving from left to right. This is our representation of a chemical reaction. These are different substances. Methane is flammable hydrocarbon, and oxygen is just the stuff we breathe. And these have their own identity. And when we combine them and they react, this equation tells us that they produce these products. Now, there's one other thing that occurs, and this it's taken decades to understand what is actually happening. In medieval times, most of what they did was by recipe. So the master alchemist would pass on his knowledge to a student, an apprentice. But if you didn't learn it from that master, then you didn't know the recipes that would give you the end products. Now we know that when substances interact, they don't interact based on volume. They don't interact based on mass. They interact based on individual atoms. So that's what we're representing here. This methane is a combination of two types of elements, 1 atom of carbon and 4 atoms of hydrogen. That makes the compound. And oxygen, of course, is a diatomic gas. That's one of those elements that you had to learn were diatomics, along with nitrogen and fluorine and chlorine and bromine and iodine, and hydrogen. Those are all diatomic elements. So we always write them in pairs like this. And when they produce their products, now all we've done is rearrange the atoms. John Dalton was part of his theory, the atomic theory. He said that during a chemical reaction, these atoms just rearrange. So we get the carbon is still there, it's right there, right? We haven't created any new carbons, we haven't destroyed this carbon. These 4 hydrogens should be over here, but there are only 2 on that side. So you can see that based upon the number of atoms of each element, this equation is not balanced. If we take this equation as is, we're saying that 2 of those hydrogens were destroyed in the process, which is impossible. So we're going to have to talk about balancing equations here pretty soon. And likewise, 2 oxygens now become 3 oxygens. So that can't happen. All right. Right, I've already said that. We can't create atoms, we can't destroy atoms during a chemical reaction. They just trade partners, they rearrange. And we have to have, in order for the equation to be balanced, we have to have the same number of atoms of each element on opposite sides of the arrow. All right, we'll talk about polyatomic ions here in a minute, relative to the balancing equations. This is your, this is the publisher's idea, the author's idea of trying to make sense of what's going on. If you count up the atoms of each element, you find that it's not balanced. And then when you balance the equation, what you need is the same number of carbons, but we need extra hydrogens. So in order to have extra hydrogens, we can't have just 1 water molecule. We need 2 of them. So if we have 2 of them, now we have 4 hydrogens, right? And we also have 1, 2, 3, 4 oxygens. That means instead of 2 oxygen atoms on the reactant side, we need 4 oxygen atoms. Right? So if you write it like that, it takes a lot of space, and it's easier to write it like this, to use these numbers in front of the elements or the compounds. Those are called coefficients, those numbers. Once you have decided what are the reactants and correctly write the compound formulas on the reactant side and the product side, then you cannot change the subscripts. Those are chiseled in stone, as they say. The only way that you can change numbers of atoms is with coefficients. You can say, okay, I need more of these, but I can't change that, so I'll have to put a 2 up here. So that's where this pair of oxygens is incorporated into the equation. And I'm gonna introduce you to a method for doing this balancing that's not foolproof, but it makes the whole process a lot easier. Okay, now we'll digress for a little bit. That reaction as written here, CH4, and I'm going to balance it now. And we've got, excuse me, oxygen, there we go, and 2 waters. So that will be balanced. And it's often customary to say, all right, what phase are the reactants and products in? Are they gases, liquids, or solids? Or are they in aqueous solution? That's another option. So this is a gas. So we put a little g with the parentheses. That's a gas. This is a gas. And with all the heat that's being produced, this is also a gas. It's water vapor. Other states that we can designate are little L for liquids, little g, well, little s for solids, where we have that yellow precipitate. Next to that compound, we would put an S for solid. And then when we talk later, we'll talk about solutions. We may use AQ for an aqueous solution. Those are the only ones that we're interested in right now. So here's an example. There's our potassium, right? Potassium metal. Now this potassium metal looks like it's in a liquid, and it is. That's mineral oil. Potassium will react with moisture in the atmosphere. It'll even react with the oxygen in the atmosphere. So we keep it submerged in mineral oil because it won't react with mineral oil, and that's safer. But when we combine it, when we take some of this potassium out, put it in the water, which is what this represents here, the solid potassium combined with the liquid water, and it produces hydrogen gas here. And it also produces this compound, potassium hydroxide. And notice that there's so much heat produced that the hydrogen gas ignites when it reaches the atmosphere, when it combines with oxygen. That's a separate reaction. This reaction only defines what happens in here. There's another reaction that goes on up here where the hydrogen is reacting with the oxygen to produce water. Okay. So let's see if we can make some sense of this scenario. So if we shine blue light on a mixture of hydrogen and chlorine gas, right? So it's helpful to, as we go, just extract from that problem what it's telling us. It's telling us that hydrogen gas is in the presence of chlorine gas, right? Both of those are diatomic. Okay? If you read this problem and you write that as H and Cl only, then you will not get the correct results. You have to write it as diatomic. That's why in the beginning, when I gave you the elements that I wanted you to memorize, there were some of them with a blue background. Those are the diatomics. You write those as H2Cl2 in this case. And this is one of the reasons you do it, because in a word problem, it's not going to tell you that there are two hydrogen atoms. Hydrogen gas has to be diatomic, chlorine has to be diatomic. Okay, these elements react explosively when we shine a blue light on them. So what are they going to do? Well, it's going to tell us they make hydrochloric acid, gaseous hydrogen chloride. Okay. That's the unbalanced equation. We've accounted for the reactants and the product and the correct formulas for each. So the unbalanced equation would be this one, right? You can tell it's not balanced because there are two hydrogens here, one there, two chlorines there, and one there. Okay, so this one is fairly easy to balance. All you need is a coefficient right there. And you got two hydrogens, two chlorines, and we're good. Some of them are really easy, some of them are a little more difficult. All right, I've already said that, so I'm not going to stop there. Most of the time, when you're given a problem to write an equation like this, you will be given both the reactants and the products. Right? Because under different conditions of, say, temperature, pressure, other factors like catalysts maybe, or well, the sky's the limit. Under different conditions, you might get different products. So we generally give you both the reactants and the products so that you can write the complete equation. There's one exception, and it's too early to talk about it right now, but we will eventually. So once you're given the reactants and products, which are determined by the researcher. Sometimes researchers do conduct reactions and they don't know what the products are going to be. So they have to take the products and analyze them to determine what they are. And sometimes it's easy and sometimes it's very tedious and difficult. But for our purposes, you'll usually get both reactants and products given to you. Then you have to write the formulas correctly. If I give you a name, like if one of the products is like this one, ammonium chloride, right? We studied in previous chapters how to write compounds. So what is ammonium? Ammonium is a polyatomic ion, right? It has a 1+ charge. Chloride has a -1 charge. It's a halogen. So to write this compound, and it would be a type 1, that's a fixed charge. So we just balance the charges, and the compound would just be written like this. That would be your compound if it were given to you as one of the reactants. Okay. So once you've written the chemical formulas for all the reactants and products and put them in their proper place, then we can turn to balancing the equation. But you can't do that until you write the formulas correctly. And if there's any state involved, gas, liquid, solid, aqueous, you should write that in there also. It may have a bearing on the problem. It may not, but it may have. So how would we write hydrogen gas, oxygen gas combined to make liquid water? Well, they've given you the formulas, but you should be able to write those yourself, right? H2 is hydrogen gas, O2 is oxygen gas, and water is H2O. Okay, we're not going to write it yet. Yeah, we are. We're going to write it next. There we go. So this is the unbalanced equation where you've just written the reactants and products correctly and assigned their states. A gas produces a liquid. Then what far too many chemistry textbooks say at this point is to balance by inspection, which in my estimation is a cop-out. They don't want to take the time or the trouble to teach you how to balance equations. So they just say, balance by inspection, go on to the next topic. We're going to stop and learn how to balance equations. All right. So rather than labor on these diagrams, I'm going to go to, let's see, I'm going to go to my method. I will make a point here. Once you balance the equation, you want the simplest whole number ratio. These coefficients can be viewed as ratios, right? For every 2 hydrogen molecules, you need 1 oxygen molecule, and that produces 2 water molecules. That's the simplest whole number ratio. It cannot be reduced any further. And once you balanced it, that ratio is fixed. So you could just as easily say, instead of 2, 1, 2, you could say 4, 2, 4. Or you could say 8, 4, 8. But the simplest whole number ratio is 2, 1, 2. All right. Now, the next slides have a bunch of helpful hints. They're not step by step how to balance an equation. I'm going to do that on the board. And in fact, what I need is something to work from. That's a good one. Let's do that one. Now, this is a balanced equation, but I'm going to show you how we got there. Let's say we're going to take glucose, and there's an error. See that error right there? That should be a subscript. It should be down here. Glucose, C6H12O6. That's the same stuff that floats around in your bloodstream and delivers energy to all your cells, and is under the control of several systems, but the one that seems to go wonky most often is insulin, right? When your pancreas is not making enough insulin, or your cells are resistant to the insulin that would help them metabolize glucose, then you get diabetes. So this is the same stuff. And this is the overall reaction that occurs in your cells. Combine glucose with oxygen and you make carbon dioxide and water. Right? Now, if you do that as a chemist, you can put some glucose in a spoon and set it on fire and you get the same reaction. Only it happens quicker and hotter. So in your body, this reaction takes place in many elementary steps so that it doesn't generate a whole lot of heat at once, and your body systems can access energy more efficiently. If you did that, if you burned it like a chemist does in your body, it would destroy the cell. So, but this is the overall reaction that occurs. Glucose plus oxygen. Notice I left a space here for my coefficients. Creates carbon dioxide and water. Now, because of the space, I left off the states, the solid, liquid, gas designators. And in this case, we don't need them to balance the equation. Okay, here's what I call my budget method. I'm gonna set up a budget, and then we're gonna balance the budget. So in order to do that, I have to find out what are all the elements that are in this equation. There's carbon, so I'll put carbon right here. And there's hydrogen, and there's oxygen. Okay. Now on this side, I'm going to do a preliminary tally. So how many carbons do I have? Well, I have 6. And I have 12 hydrogens. And I have 6 plus 2 is 8 oxygens. On this side, I've only got 1 carbon. And I've got 2 hydrogens. And I've got 3 oxygens. Doing it this way will tell you instantly whether or not your equation is balanced, because every time we make a change up here, we're going to change these numbers. And when it's balanced, you can see they'll be the same all the way across. Okay, so the next question is, once you've written these correctly and you've done your tally, where do you start? Well, in this equation, there's one place you don't start. You don't start with single elements, individual elements. You want those to be last. That's one of those hints. This is your first hint. You want to save that one till last. The reason being, when you put a coefficient in front, it has an effect on everything that's in the compound. So if you put a coefficient in front of this one, it would change the number of carbons and the number of oxygens. Okay, so you say this one to last because once you need to put a coefficient in front of this one, that's the only one it changes. Okay, so where do we start? Well, we're going to leave the oxygen out, so we can either start with hydrogen or carbon. It shouldn't matter where you start. It's just that if you, with experience, and you learn to start certain places, you'll get to the end quicker. But eventually, if you wrote your compounds correctly, then you should get to a balanced equation, whether it takes you 2 steps or 10 steps. Okay, so I'm going to start with carbon. If you can't decide, just start at the top. So we need 6 carbons over here. I'll put a 6 right there. That means 6 carbons. It also means 12 oxygens, but I've already got one here also. So that's 12 plus 1 is 13. Okay. So now we can see the carbons are balanced, and we've thrown the, we need to do the hydrogens next. The reason I'm saving oxygens to last, one of the reasons is I've got this factor up here to make it final adjustments. So I'm going to go with hydrogens next. So I've got 12 hydrogens here. I need 12 hydrogens here. So that's 12 hydrogens. Now I've got 6 oxygens and 12 oxygens, which is 18. 18 oxygens. Okay. Now, notice oxygen occurs in 2 different places here. So which one do we use? I think it's more efficient to use that one. Because if we do anything with this one, it changes everything else. And we're back to the drawing board. So let's use this one. Okay, we've already got 6 here. So 6 from 18 is 12. We need 12. So there you go. That's 12 plus 6 is 18. And you can see 18, 18, 12, 12, 6, 6. Our equation is balanced. That's my budget method. And the first trick on the list, or the first hint, is save that one till last. Okay. Let's see. Very often it's also good to save water to last if you can, but definitely save the elements to last. All right, so here's one. Let's see, this is a different equation. All right, so this is going to show up another hint, another trick. So if we start with this one, C8H, I'll tell you what, let's do a different one than that one. This is octane. This is the primary ingredient that's in your gas tank. Right? So I'm going to take, instead of this hydrocarbon, C8H18, I'm going to take a different one. I'm going to say maybe C5H22. No, C5H12. That's pentane. Okay, and we're going to burn it, right? we're going to have a similar reaction to this one, only I'm using a different compound. Right? The process will be the same, but it will have probably different coefficients. So this is also going to produce carbon dioxide and water. Okay, so the first thing we do is say what elements are here? Carbon, hydrogen, and oxygen. That covers everybody. So now we tally 5 carbons, 12 hydrogens, 2 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Okay. So I'm going to start with carbon again. We've got this one we're going to hold till last. Go carbon. So I need 5 here. Oh, excuse me. No, I don't. Yeah, I do. What am I thinking of? I need 5 here. 5 times 1 is 1, that's 5. And that changes the number of oxygens. So that's 10 plus 1 is 11. Okay, now hydrogens. We've got 12 here. I need 12 on this side. 6 there. So that's 12 hydrogens. Now I've got 6 plus 10 is 16. Okay. Let's see if I did that right. 5, 5. You know, sometimes it's helpful to know that you've counted them correctly to begin with. Just total them up. So 5 plus 12 is 17, 18, 19. So that's 14 and that's 19. This would be 1, 2, 3, 4, 5, 6. That's 1, 2, 3, 4, 5, 6. Okay, so I got started right. Now 5 carbons. Yep, 5 carbons. That gives us 10, 11 oxygens to begin with. And now I need 12 hydrogens. So I do 6 there. That makes 12 hydrogens, but it makes 6 plus 10 is 16. Okay, we're good there. Okay, so now we can balance the oxygens. This is not doing what I expected it to do. I'm going to finish it, of course. We need 16 oxygens, and oxygen only occurs in one place over here. So I need 8. That's balanced. I didn't get to use my trick. All right, so let me choose a different one. I'm going to choose a different hydrocarbon. In this case, I'm going to say C6, H14. And that one is hexane. Okay, let's start again. We've got 1 carbon, 2 hydrogens, and 3 oxygens. And we got 6 carbons, 14 hydrogens, and 2 oxygens. So that's 16, 22. 6, 22, okay. 1, 2, 3, 4, 5, 6. That's 6. Okay. So I'll start again. 6 carbons, right? And now 12 plus 1, 13 oxygens. Okay, that's right. Hydrogens. I need 14 hydrogens. So we'll put a 7 there. That makes 14 hydrogens plus 7 oxygens plus 12 is 19 oxygens, right? All right, 7 plus 12 is 19. Yeah. Okay. Now we've got this one balanced, this one balanced. How do we balance the oxygens? There's our next trick. Use a fraction as an intermediate step. You need 19 oxygens and they only occur in one place. So I'm going to use 19 halves. Right? The oxygen molecule is like this. Right? So if I have 19 of those, I would actually have 36. So I'm going to take half of that. So I'm going to take half of that. Now I've got 19 of those. That means the equation is balanced. The problem is we don't have whole numbers now. So the way you get back to whole numbers is get rid of the fraction. So how do you what do you multiply by a fraction? What would make that a whole number? Well, multiply by 2, right? That means the 2's cancel. And there you go. Okay, so that's what we're going to do. We're going to multiply that entire equation through by 2. Remember, once we've balanced the equation, and look, it is balanced, as is, then these coefficients, these ratios are fixed. And anything we do to one of them, we have to do the same thing to the other one. So if we say 2 times this one, then there's always a 1 in front of that. That means now we've got a 2 here. We've got a 19 there. We've got a 12 here. And we've got a 14 here. We've used that too. So the ratio now is 2, 19, 12, 14. That's the fraction trick. And that same method was used for this example as well. All right, let's see what else we got. This one is a little more difficult. Okay, so in this case, for this hint, we have ammonia gas reacting with oxygen. So we're effectively burning ammonia. And it's yielding nitrogen monoxide plus water. Okay, so we've got our compounds written, our compounds and elements written correctly. Now we need to do our tally. So there's nitrogen in there, there's hydrogen, and there's oxygen. And the original tally is 1 for this, 3 hydrogens and 2 oxygens. On this side, we have 1 nitrogen. We have 2 hydrogens. And we have 2 oxygens. Okay. So it looks like the hydrogens are the only ones that are out of whack. But hydrogen here is in a compound. Hydrogen here is in a compound. So anything we do to adjust the hydrogens is going to mess the rest of them up, which is unavoidable. So here's what we're going to do. The problem is also that the hydrogens are odd and even. So we can't say 2 times that will give us the right number of hydrogens because that's 3, that'd be 4, or 2 times this would be 6. Right? So when you have a situation like that, where the element is odd even, and in one place on this side in a compound, one place in this side in a compound, and no other places, but just 1 on this side, 1 on that side, I would try cross multiplication. Right? It's a mathematical trick. Take this 2 and make it the coefficient here. And take that 3 and make it the coefficient here. So that gives you 6 hydrogens here, 6 hydrogens there, and then we'll deal with the others, right? 2 times 1 is 2, okay? And 3 times 1 is 3. Okay. So now we can deal with the nitrogens. We need 2 nitrogens. That gives us now 2 oxygens there and 3 oxygens there, which is 5 oxygens. We've got nitrogen, hydrogen. Now oxygen needs to be balanced. And notice oxygen is all by itself here. And we've got a prime number and a prime number, right? There's no factor that will bring them both together. So we're going to use a fraction again. We need 5 oxygens on this side. 5 halves will give you 5. Okay. Another intermediate step with a fraction. So you know what to do now. You get rid of that 2 by multiplying the whole thing through by 2. So that makes this 4. That makes that 5. This is 4. And this is 6. So now the whole number ratio is 4, 5, 4, and 6. And we know that that's the simplest whole number ratio because there's no divisor that will get rid of that 5. Right? Remember, prime numbers, they're only divisible by 1 in themselves. So that's as low as we can go. Let's see, is there more? There's more to it than that, isn't there? I thought there was. You would have to use multiply by 2 to get rid of the fraction. Okay. Now the next trick or hint has to do with polyatomic ions. If you have compounds that are composed of 1 or more polyatomic ions on the reactant side, and the polyatomic ion is intact on the product side, it has not been broken apart, then you can use that polyatomic ion as a balancing unit. Rather than write the individual elements, you write the polyatomic ion as one of your factors for your budget. Here's an example. We have ammonium phosphate. Let's see, is that written correctly? Ammonium is a +1, phosphate is a -3, so we need 3 pluses to balance it. Yep, that's right. Calcium chloride is another reactant. Calcium is 2+, it's an alkaline earth. Chlorine is a halogen, it's -1, so we need 2 of those to match 1 of those. That's correct. Calcium phosphate. Remember how we write calcium phosphate? It's a 3- here and a 2+ there. So we use that cross multiplication trick, just like we did when we were balancing. The cross multiplication we used for balancing equations, we also used it to write compounds. So bring this 3 over here and this 2 over here, and that gives us 6 minus 6 plus, we're balanced. Ca3, PO4 taken twice. So that was written correctly. And then ammonium chloride, we did that one earlier. Okay, notice this ammonium is intact on the product side also. And this phosphate has not changed on the product side. So we can use those as balancing units. And I've set up a table here, so I don't have to draw the whole thing out. And here we have ammonium from there, phosphate from there, calcium from there, chlorine from there. And then we do the initial tally. Right? 3, 1, 1, and 2. Right? We say 3 ammoniums, 1 phosphate, 1 calcium, and 2 chlorides. And then we do the other side. These are the initial counts. 1 ammonium, 2 phosphates, yes. 3 calciums, correct. And 1 chloride. Okay, so our initial tally tells us that definitely this is not balanced. So where do we start? Well, we don't have any separate elements to hold in reserve. So we just start where we want to. I think in this example, I started with the calciums. Yeah. So these little red letters say this is the first step. This is my first step. And I'm going to balance the calciums. I need 3 calciums on the reactant side to balance the product side. So there we have 3 and 3 match. So in that case, we've changed the chlorides. So now we have 6 chlorides. We have to tally that. Okay. Now we can go on the product side and balance the chlorides with a 6. Right. So we retally both the ammonium and the chlorides. There we go. So now we got to come back on the reactant side and balance the ammonium. So we've already got 3 in this unit. So if we put a 2 out here, that will give us 6 ammonium. Here we go. We got 6 ammonium, but we've changed the phosphate also. So we have to recali that. Okay, there are 2 phosphates. And if you take a quick look, 6, 6, 2, 2, 3, 3, and 6, 6. Our equation is balanced. All right. All right, so we've got some examples coming up. We'll start off really simple. So we have this example given plus oxygen yields this one. Okay. So what would this name be? We can always practice names. Oxygen, remember, is a 2-. So this one has to be a 2+. Now, is this a type 1, type 2, or type 3 compound? It can't be a type 3 because it's a metal and a non-metal. So it's either a 1 or a 2. So you look at the metal. The metal comes from a region of the periodic table that has possible multiple charges. So it's a type 2 compound. So we have to say iron charge oxide. Right? That one's obvious, oxygen. How about this one? -2. So this is a -6 total charge here. We need a +6 here. So 2 divided into 6 is a +3. So this one is iron 3 oxide. Okay. Notice what's happened here. You've changed the charge on your iron from 2+ to 3+. Right? So how do you get there? Right? Think back to the beginning chapters when we were talking about atoms and charges. How do you get to a charge? You either gain electrons or lose electrons. To go from a +2 to a +3, you had to lose 1 electron for each iron. Right? Okay, so now that we got that little diversion out of the way, let's balance this equation. All right, what do we have to work with? Just iron and oxygen. All right, so on this side we have 1 iron and 3 oxygen. This side we have 2 irons and 3 oxygens. So we have to start with iron because oxygen's already balanced. So we're going to put a 2 here. That gives us 2 oxygens 2 irons plus 2 + 2 is 4 oxygens. All right. How about this side? Well, now what we've got is a situation where we've got a 3 and a 2. So I'm tempted to use that cross multiplication. I'm not sure if it'll work, but I'm going to try it. So if I put this 3 over here, no, because we have oxygen in 2 different places, I better not use that trick. So what I need on this side, let's put a 2 here, and that'll make this an even number. Now, that won't help us any because it changes to iron. All right, I'm going to start over again. Let's leave those there. 1 and 3. That would have been the logical place to start with iron. Instead, what if well, that should work. No, that should work. Now we want an even number on this side. So we would have to do a 2, which would be 6 oxygens. Now we have 4 irons. And on this side, we need to go to 4 irons. That makes 4 plus that's 6. And 4. There we go. So that worked itself out. I was starting to panic. Did everybody see what I did there? I followed through with my original and made, let's see, and made 4 irons and 6 oxygen. No, this was 2, excuse me. I made this 2 first. And then I had to go balance these out. So I put a 2 here, and that changed this one to 4. Okay. And sometimes that happens. It looks kind of squirrely, but if you just plug through, it'll work itself out. Right. So when this says the sum of the coefficients, what are the coefficients? All right. Well, we got a 4 there. We got a 2 here. So is the answer 6? No. You got 1 here. There's an understood 1 right there. So that means 4, 1, 5, 6, 7. The sum of the coefficients is 7. All right, here's another one. Which of the following correctly balances the chemical equation given below? There may be more than one correct balance equation. Explain what's incorrect about it. All right. So we got a calcium oxide plus carbon yields calcium carbide plus CO2. Anybody has grandfathers probably, or great grandfathers that were miners. They know calcium carbide. The lamps that they used to use underground in the coal mines had a little can in them, and you put crystals of calcium carbide in there and add water. And when you add water to that, you get acetylene gas, and that's what they light, what they used to light. Of course, that's an open flame, and it didn't take them long to figure that open flames were not a good idea in coal mines. Coal dust and methane pockets. So they stopped using this and went to insulated sealed electric lamps. Anyway, this reaction takes calcium oxide, lime, plus graphite, carbon, and makes calcium carbide and CO2. So let's see, we've got calcium and oxygen and carbon. So one calcium, one oxygen, one carbon. That was easy. One calcium, two oxygens, and three carbons. Okay. So we're going to hold this carbon till last. And the next one available is oxygen to balance. So we got two oxygens there. We need two oxygens here. That gives us two oxygens. It also gives us two calcium. Okay. Now we got to balance the carbons. Excuse me. Calcium. We need two calcium here. So that gives us two calcium. And then we have 4 plus 1 is 5 carbons. Okay. So now we're going to use the fraction trick. We need 5 carbon. Actually, we don't need the fraction trick because that's only a single element. Just a 5 there. Yeah, that works. So the ratio here is 2, 5, 2, 1. So which is the best one? The best one is that one, 2, 5, 2, 1. Now the others give you the same ratio of 2, 5, 2, 1. Like that one, but we use fractions, right? So that's not desirable. Or we use bigger whole numbers, just multiply through by a factor, 4, 10, 4, 2. And then of course the top one, excuse me. Well, let me go back. Okay. Oh yeah, there we are. The top one is wrong. Right? 1, 3, 1, 1. That's just entirely wrong. And you can see there are 3 carbons here and only, well, 3 carbons there, 1 calcium there, 1 calcium there. You know, that looks like it balances. 2 oxygens, 3 carbons. Are these written correctly? Yeah, they're written correctly. Calcium, calcium, 2 oxygens. Oh, that's the problem right there. In order to balance this equation, some smart aleck changed the subscript. That's not the right compound. Right? That'll never work because calcium doesn't have a 4 plus charge, which would be required if you had 2 oxygens. Okay, so 1 is wrong because we changed the subscript. All right. So when balancing a chemical equation, which of the following statements is false? All right. Let's see what the statements are. Subscripts in the reactants must be conserved in the products. That doesn't make any sense. If you have to conserve the subscripts, then you have to write the compounds incorrectly. Right? A can't be right. Coefficients are used to balance the atoms on both sides. That's true. Yeah, coefficients are the way to do it. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. Once the equation is balanced, then anything you do to one of the coefficients has to be done to the others. So that was true. And phases are often shown for each compound, but are not critical to balance an equation. That's true. So the only false one is that one right there. Okay. We're just restating the obvious. The number of atoms of each element have to be the same on both sides. Subscripts cannot be changed once the compounds and elements have been written correctly. After that, the only way to change numbers is with coefficients. Now, what does that balanced equation tell us? It tells us the ratio of the number of molecules which react and are produced in a chemical reaction. In other words, that ratio is fixed. Once you've balanced the equation, then that is the ratio for that reaction. And it can be interpreted, up to this point, we've been interpreted as individual molecules and atoms. Right? But we're going to introduce, let me see, I think it's next chapter. Maybe not. When we get to stoichiometry, then that's when we'll add a meaning to those coefficients. You can use fractions, but we prefer whole numbers. So if you use a fraction in balancing, then as a final step, get rid of the fraction. Oh, okay. So I was clairvoyant. Stoichiometry right around the corner. So what is stoichiometry? Well, what it means is that once we've balanced an equation, the equation tells us the number of atoms of each element that goes into reactants and ends up in products. But we don't have any equipment in the lab that will measure in numbers of atoms. So we have to use things like mass. We use a balance, or we use, we're going to learn in the next chapter how to use solutions and determine how much of the reactant goes in as a solution and how much comes out. So stoichiometry, as a first step, we're going to focus on masses. What mass of reactants produce mass of products? And Lavoisier, back in the 18th century, has already proven that when you put reactants together and you total their mass, then gather all the products together, and their mass is the same number. So mass of reactants equals mass of products. He didn't know at that time that that law was true because the same number of atoms of each element is present on both sides, right? So that explains the mass, the conservation of mass. But for doing stoichiometric problems, we need to know how to work between numbers of atoms and molecules and masses. Right? That's the trick. Oops. Oh, so we're not going to do that today? Hold on a second. Let me check down the road just a second, because I want to see where we're headed. Yes. Okay. So hang on to that concept of stoichiometry. That comes in chapter 9. We're going to do chapter 6 and 7 for this exam and get that under our belts. And then chapter 9, we're going to study how to do that stoichiometry. So that's in the future. Okay. Any questions? Okay. I had several handouts, and in addition to the PowerPoints, in Brightspace, you'll find this other document. It's based upon those slides that I showed you, the helpful hints in balancing equations. That's available in Brightspace also. And then you have your usual review document and worked problems and the review key. So those are there. And then this one other one. We'll get to this one on Thursday. This will be useful in talking about solutions. This is a solubility chart. So you don't have to deal with this yet. You may want to print it out and have it ready for Thursday. But those are all the handouts that I had for today.